So in this video we will solve an integer linear programming problem whereas one of the constraint is nonlinear using MATLAB. So suppose you have a maximization problem where you're gonna be maximizing z equal to 150x1 plus 160x2 plus 180x3 subject to 1x1 plus 1 over 3x2 plus 1 over 4x3 less or equal to 1. The second constraint is 2x1 plus 2x3 is less or equal to 2. These, the first two constraints, are a linear constraint. The third one is x3 is more or equal x1 by x2. So this is a nonlinear constraint, but it still is a convex constraint. So we want to change it into MATLAB standard form. So multiply both sides by -1. So this is becoming minus x1 is less or equal minus x1 by x2, and still is not acceptable in MATLAB, because in MATLAB the nonlinear constraint should have all the variables, the quantity and the variables are within the left hand side, and the right hand side should be always 0. In MATLAB you will find out your nonlinear constraint can be defined in two forms. The first one is C. So C is equal to x1 by x2 minus x3. This will be meaning you have inequality, so it will be always less or equal to 0. The second one will be C equal. So that's mean what you have variables and equations with their quantity will be always in the left hand side. So supposedly the same problem, we having x1 by x2 minus x3, so this is will be equal to 0. In MATLAB you're gonna define it in separate manuscript. So here you have the function. So this is a new thing. When you define in MATLAB, usually you will put only one variable. Here we will put it in array. So C and C equal will be equal the name of your function, which is the name of your constraint. So in our problem, C is equal to x1 multiplied by x2 minus x3. So this constraint will be recognized within MATLAB as x1 multiplied by x2 minus x3 is less or equal to 0. But the other one, C equals, will recognize it as x1 by x2 minus x3 is equal to 0, which is we didn't have it in our problem. Then we're gonna define the MATLAB code. So basically what you're gonna do is the same thing you have done it with integer programming problem, but because we have the nonlinear constraint, we will be implementing both fmincon optimization toolbook with the branch and bound methodology. So the first thing is you're gonna make a manuscript for fmincon, which is very similar to linear prog and integer linear prog. So you're gonna define your function. Basically fmincon is using the minimization as the linear prog and integer linear prog. So here you're gonna switch it into minus 150 by x1 minus 160 by x2 minus 100 by x3. So the different thing here, you will set up the function as it is. In linear prog, you need only to set up the coefficient. But fmincon can handle any type of function if they are, even if they are in non-linear form. So basically fmincon is a library of optimization toolbox. So it might, but all of these toolbox doesn't use evolutionary algorithms, which have another toolbox in MATLAB libraries. So basically one of them is gradient descendant, and there is another ones, maybe some of them using Bayesian method or using a research area method. So in our program right now, we're using an integration between Bayesian and a gradient descendant method. So you need to set up an initial value to enhance your search. Then you have the constraint. The linear constraint are defined the same way you have defined it in linear prog. So in the original problem, you have 1 x1 plus 1 of the 3 x2 plus 1 over 4 x3, and the second one is 2 0 2. So your matrix should be 1.333.25, and then the other row is 2 0 2. You can notice it in the MATLAB over here. Then the right hand side is 1 and 2 when you go back to the original problem, so it's 1 and 2. So we don't have any equality constraints, so we leave them blank. So we always start up with a 0. So but this is gonna be updated based on the branch you have reached. Then the upper one is opened unless if you have a binary integer programming, so you're gonna set up to ones, but in this problem you leave it empty. Then here, the new thing here is you're gonna set up the non-linear function in this syntax. The different thing is fmincon doesn't handle in any way the integer programming problem. So there is no a magic code or any advancement. You can put it inside like an option, then it will be solved by default. So the thing here, we're gonna integrate the branch and bound method with the fmincon code to have the final solution. So if you have a small scale problem, you can use this one. If it's more complicated one, then it's advised to go for the evolutionary algorithm or any heuristic technique. So we can start up our code. So it already the code give us the Bayesian matrix and the gradient matrix. So let's see if the solution was optimal. So the 8th iteration give us the solution, whereas there is no special condition, with value of 540.36. So we can tell, because the objective function is having a non-fractional coefficient, so one of our decision variables is not integer. So we can find out our values of x. So x equal to 0, 2.25 and 1. So luckily we have two integer variables. The only one is not integer. So we can set up our branch and bound solution over here. So here we have the first branch. So z equals to 540 with x1 equals to 0 and x2 equals to 2.25 and x3 equals to 1. So we don't have a problem with x1 or x2. but we still have a problem with. So how here our starting point for solving branch and bound problem. So we end up with a z is around 540, where x1 equal to 0, x2 equal to 2.25, x3 equal to 1. So we don't have a problem with x1, we don't have a problem with x2, 3, but only we have a problem with x2. So the interval gives us a problem when x2 is in between 2 and 3. So we need to reformulate our problem with adding a new constraint which make x2 not within these two values. So the first one, we will try to search when x2 is less or equal to 2, and the other one when x2 is more or equal to 3. Then you're gonna implement each one of these branches alone in MATLAB. So let's start with this one. So the only thing you need to update is your boundary condition. So you're gonna go to the lower bound, so we know there is nothing to do over here. For the upper bound, you're gonna set up for x1 to be a very high number. You know it will never reach it out. So x2 will be at most 2 and x3 will be a very large number. Then you're gonna run the code again. So let's check out the z value. So it's reached out 500 with x1 equal to 0, x2 equal to 2, and x3 is 1. So the solution as an integer programming problem is optimal. So here our solution, so z equals 500 with x1 equal to 0, x2 equal to 2, and x3 equals to 1. So let's check out the other branch. So the first thing you're gonna need to nullify your original problem. So you're gonna return it to your original solution. Then you're gonna update it over here. So the only thing we need to make the x2 is more or equal to 3. Then we're gonna run it again. Hopefully we can get an optimal solution. So here x1 is integer and x2 was solved, but x3 wasn't solved. So we need more branches. So we know from previously we have this solution which was optimal. So z equal to 500 with all axes are satisfactory. So we know the other one when we add x3 to more to equal x2 more equal to 3 is not optimal. So this is the second optimization problem. So here the thing so x3 was between 0 and 1. So we need to update this problem. So we have two new setup of problems. So we are ready in the second optimization problem. So we have x3 only can have value of 0 right now because it cannot be having a less than 0. The other problem is when the optimization problem over here is x3 is more or equal to 1. So let's solve this problem, then check out the second one. So we know for x3 right now, so the lower bound and the upper bound is 0. So 100, you can give it also any large number, then here 0, then run it again. So right now it gives us another problem over here, so we need two new branches. So it's solved for x3, but we have the problem now with x2. So x2 should be between 4 and 3. So we have the optimization problem number 3 with adding x2 is equal to 2 right now. So we don't have any other direction. The other one is for the third optimization problem for x2 is more or equal to 4. Let's solve it for this one. So let's run it. So you can see it gives us the second flag, which means the solution was invisible. Even if it gives us amount, but we have already violated one of the assumptions, so we can skip this branch. Let's go back to these two branches. So x2 is equal to 2. So we are already having two bounds right now to set up to be. So x3 will be only 0 and x2 will be only 2. Let's update our problem. And run it again. So 320, and let's see if we have, yes, so all of them are integer. So here the z is equal to 320. Let's check out the last one. So it's invisible. So you're gonna dismiss all the invisible branches and only compare the visible one. So we have z equal to 320 and z equal to 500. So you're gonna pick this one. So this is the optimal solution.